For a moment. Okay, so folks, we're supposed to have Professor Amitawa Das present today, but he was giving an invited talk at a conference yesterday, and he's flying, and his original landing time was 1 p.m., but clearly he's in the middle of the flight, so he can't present. But today we have Parth Patwa. Parth, this Parth. Okay,
Sorry.
Parth is at Amazon now, and he I guess he's going to substitute on short order. So he's not going to talk exactly about the visual language model, but he's going to talk about RAG that involves multimodal data, and so some aspects of things we would have covered if Amita were to give talk would be covered. So have you started on recording? Yeah. So I'll give it to Parth. If anybody wants to ask some questions related to job at Amazon, he's at Amazon, and so you could ask him that too towards the end if you want. Okay. All right, Parth, over to you.
Okay. Yeah. Hello, everyone. Thank you very much, Professor Sheth, for giving me this opportunity. So today I'll be covering a survey of RAG, some advanced RAG topics, and the applications of RAG. So I'll go over basics of RAG, some advanced RAG techniques, routers, agentic RAG, graph RAG, multimodal RAG, evaluation of RAG, and applications of RAG. So what is RAG? RAG stands for Retrieval Augmented Generation. If we have an LLM, and if the question is who is the current president of the United States, but if the LLM was trained maybe on data which ends 10 years back, then the LLM will give us the wrong answer. And LLMs also hallucinate. They sometimes make up answers and provide incorrect facts. So what RAG does is it ensures that the LLM have the recent most knowledge and provide facts to it. So we have, let's say, a collection of documents. So first what we'll do is we will break down the documents into chunks and convert them into dense embeddings. And these embeddings are stored in a vector database. So when a user query comes, we embed the query and retrieve the top key relevant documents based on the similarity metrics with the document embeddings. And these documents are given to LLM along with the question to generate the answer. So these documents are provided in context. And this is how it works at the runtime. A query comes, which is embedded. The embeddings we compare with the embedding stored in the vector database. From there, we fetch the relevant context, which is like relevant chunks or paragraphs, and they are appended to the query and given to the LLM for the response. And the offline step is all the documents are embedded in using the embedded model and stored in the vector DB. So as I said, LLMs could have older data, but in RAG, the documents have the latest data. And if you are to fine tune or retrain an LLM, it is an expensive process. But if the documents get updated, then indexing them again is a much easier and cheaper process. And furthermore, this reduces hallucination because LLMs cite the source documents with result. So overall, it's cost effective and improves user confidence. We can, some important hyperparameters are like embedding model, top K, and temperature of the LLM, and so on. So this was the basics, so this was the basics of RAG. Now I'll go to some advancements in RAG. So one is Recomp is a paper where they are compressing the retrieved documents, because if you're adding all the documents, then the context increases, which increases the cost. So what recomp proposes is that all the context documents we take pass through another LLM and compress them to get a summary. And this summary is given to the LLM. So they experiment with two compressors, extractive and abstractive. So this is how the pipeline looks like. The query comes, we retrieve the document. It is given through a compressor to reduce the size. So and that was given instead of these original documents. So this way, LLM has less info and the context is faster, and the inference is faster, and the information is also relevant. So the to train the extractive
How do you,
compressor.
Parth, how do you make sure that the additional information provided through retrieval is going to cover the limitation of the original LLM training or the vector database? I mean, how do you know that indeed it would have covered the latest information for the query you are going to ask? Are you just going to guess?
So the documents, we have the control on what documents we give for the embedding. So there could be closed source RAG where the documents are prefixed, could be, let's say, the policy documents of a company, or we could have an open-ended RAG where we add a tool to also access the web search in real time. Does that make sense?
It's okay, go ahead.
Thought, I think also another, I mean, I'm not sure like whether I'm repeating the same question, but when I'm retrieving the data through an LLM, whether it is bringing it from the original document or it is the summary document, because the summary is summary, right? Where the content chunk is sitting in the original document.
Yes. So the vanilla RAG will give the entire document. There is no summarization. This recomp is one advancement where the paper proposes that, hey, instead of giving the entire documents, let's give a summary of the documents. And they show why it is better than giving the entire documents. So on training, they have, after training their method which compresses the documents, they have shown results on multiple benchmarks where the summary provides better results than the baselines or than not providing the summary. This was one of the methods for improvement on RAG. Then another group of researchers proposed self-reflective RAG, which is a very useful technique because many works are based on this. So to enhance the quality and factuality, which is our main goal, the framework will train LLM adaptively to retrieve passages on demand and then reflect on those retrieved passages, generate from those multiple passages, and also again reflect on the generation. So what happens is first we are determining if we need the retrieval. If we need the retrieval, then we call the retriever model on demand, and then multiple documents are retrieved, and self-RAG concurrently processes each of the retrieved passages. Each passage is individually evaluated for the relevance, and corresponding outputs are generated, and then the corresponding outputs are again criticized by the LLM. So how it would work is, let's say if the question is how did US states get their names? First, it is retrieving multiple documents, and then the critiquer is choosing like which of these document is relevant or irrelevant, and then only using the relevant documents, we are generating the response. So yeah, similarly, using this they show that self-RAG is much better than vanilla RAG across multiple baselines. And this sort of is inspired by like chain of thought reasoning. And so yeah, so we have a confidence threshold, and based on like so there's a trade-off between the accuracy and the efficiency. If you're allowing all the documents, the efficiency might go down, but the accuracy might increase, and vice versa. Then we have another method called corrective RAG, where we are training a retriever evaluator to check how good the retriever is. And the benefit of CRAG and self-RAG is that they're both plug and play. Like they can be, like you can have both corrective RAG and self-RAG in the same system. So here, one of this possibly answers the previous question, that corrective RAG is utilizing web searches to augment the retrieval results. So the retrieval evaluator is trained in a supervised manner by fine-tuning T5. And this is how their process works. So first we retrieve the documents, and then the evaluator is telling which document is correct, ambiguous, and incorrect. If it is incorrect, further enhancement is that they are stripping out irrelevant passages from the retrieved document by again using the evaluator. And for the documents which are ambiguous, we are augmenting them with web search. And for those that are incorrect, we are just giving the web search. So the generator takes everything, the correct documents, ambiguous document, and the web search to finally generate the response. So that was CRAG. And then we have a couple more papers on this. HIDE is a very interesting one because it is zero-shot dense retrieval. So here what is happening is that we are generating a hypothetical document which will help us retrieve the correct document. So we don't need to train any retriever or have the embeddings of the document and the query in the same space. So this is a purely unsupervised method where first we use an LLM to generate a hypothetical document, and then use that hypothetical document's embeddings to search nearest real documents. Yeah, so we are so if we are to do it in a trained manner, then we'll have to train a function to get the similarity between query and document. But in HIDE, we just need the similarity between document and document. So how it works is, if the question comes, then first HIDE will generate a response that will be given to a contriever, which is a retriever trained in an unsupervised manner with contrastive learning. And then from that, the documents will be retrieved, the real documents. This works very well on multilingual and low resource retrieval, which is especially low resource retrieval because that's where we could encounter zero-shot learning. And and finally, we have IM-RAG, which is inner monologue RAG. It is like a cyclic chain of thought reasoning in a way. So here it is trying to mimic the human inner voice, where we have a monologue on whether this answer is right or not, and then in a loop. So it has a reasoner, retriever, and refiner. I can explain with the diagram. So when the query comes, we have a trained retriever, which is retrieving the documents. And we have a refiner, which is also a trained LLM, which is refining and re-ranking the documents. And finally, we have the reasoner, which is monitoring the retrieval and the refiner, and It has questioning to question to convert the query into a question and acquire relevant documents, and also an answering module. So we are putting two LoRa adapters on the same LLM, one for questioning and one for answering. And finally, we have a progress tracker, which is trained with reinforcement learning, where the progress tracker gives a score on how much progress we have made on the answer. And this reasoner is trained in a supervised learning method. So to give an example, let's say the question is, substorm was described in qualitative terms by scientists nominated for what 7 times. So first is to figure out who the scientist was, which we do with the retriever and refiner. Then the reasoner goes on to the second question, like now replace the scientist name, and then he was nominated for what, and then finally we repeat the process to get Nobel Prize. And we can repeat this until we have the answer. So this was some of the advanced RAG methods. Any questions so far? Okay, so if no questions, let's move to routers. What are routers? So there might be multiple data sources in our knowledge base. Like there could be a database of sports, of science, and economics, and so on. So if the question comes, we need to first classify which domain does the query belong to. So a router is an LLM which classifies an input query to the relevant domain or the knowledge base, and then we query that particular knowledge base. So this helps us so we can add multiple knowledge bases and the data sources, and they could be vastly different. It could be Wikipedia, it could be like Salesforce, Slack, Gmail, and so on. And routers are not just restricted to choosing the knowledge source, but many other things like data sources, obviously, where if we need a semantic search, or do we need a text to SQL, so we can query structured database and so on. Or they can also be used to route to which component of our system the query needs to go to. And finally, this is quite interesting. If we have multiple prompts, we can on the fly decide which prompt to use for our LLM based on the query. So combining routers with RAG opens a whole new dimension for us. One such paper which uses router-based RAG is DFA RAG, where they try to solve a chatbot for customer service, where a definite finite automaton is created, and that is used to route our input query. So the DFA RAG routes conversation for a service-based chatbot to a predefined trajectory based on historical data, and each utterance corresponds to a particular DFA, and each DFA state encapsulates the historical context. So the advantage of this is that it is interpretable because we have a DFA, and obviously it's context-aware retrieval and plug and play, which means it can be used with other methods as well. So how this works is,
so when you say the router is an LLM and it routes based on the domain, is it can we use that agentic route in terms of instead of LLMs there, or
yes,
this was much the paper?
So if the problem statement is very easy, we would start with routers. Agentic RAG is what I'll cover later, but you are on the right direction. Agent is, you can consider agent as a superset of routers. So agent does everything that a router does and much more. So yeah, and yeah, just to reiterate, I'll come to agentic RAG pretty soon. So here, when the query comes, we have a DFA created of the query, and then each query has, each node in this DFA has context, which is the historical knowledge, and that is routing us to the correct historical dialogue. And using DFA RAG is much better than many other baselines, especially when we don't have round-trip states and training. I can probably skip this. And okay, that brings us to agentic RAG. So maybe you can think router RAG is like a precursor to agentic RAG. So for those who are not aware, is AI agents is like agent within LLM. We provide them with multiple tools like search engine, calculators, code interpreters. We have memory, short-term and long-term memory. Agents can decompose tasks into smaller steps and do planning. Um, After planning, they can take actions, like they can decide which tool to call, they can actually call it, and they can self-improve by reflection. And there could be multiple agents, like we could have a multi-agent system where an agent is talking to other agent and giving output based on the other agent's input. Like a side note, a fun exercise would be to program two agents to play chess with each other. But yeah, so this is the AI agent where it plans based on chain of thought, and then it has some tools which it decides which to choose, and it has memory as well. So yeah, so in agentic RAG, we can dynamically adjust the prompt, similar to routing the prompt. Then it is quite dynamic, and it is a lot more optimal and can reduce the cost. Like if you don't need some few short examples in the context, you can just remove them using agentic RAG. And it has decision making and adaptability as well. So agentic RAG is much more powerful than traditional RAG. So I'll get into some papers on agentic RAG. Golden Retriever is one. I like the title of the paper. So what they're doing, the problem statement they define is that if you are in an industry setting, like you have some company specific data, then there is jargon in that industry which is often not covered by the pre-training of LLMs. For example, RAG might mean recombination activating gene if we are looking at genetic domain. So what Golden Retriever does is we have a reflection to first identify the jargon and then clarify its meaning based on context. So first we list the jargons, then we determine the context or which domain it belongs to, then we query that particular domain's knowledge base and get all the definitions. So yeah, very nice technique where just to repeat, like we identify the jargon, identify which context it is in. So if the query is teach me about RAG, then identifying jargon is to identify that RAG is the jargon. Context is based on like, so we are in an NLP class, so it would be LLM. Query all the documents of LLM and fetch the meaning of RAG and augment the query with the meaning of RAG. So this is very helpful in retrieval because the generator would also fail if the retrieval is not good because the errors propagate. And this paper claims that the previous techniques are more focused on document like generation and less on the retriever. But the good thing which I realized is that you can just have golden retriever along with a self RAG or a corrective RAG. So yeah, this is again a workflow. Like we get a question, identify the jargon. So in this query, the jargon is POC and NAND. Then we have the sort of like a routing where we decide that it is related to the design question domain, and then we are selecting from that particular dictionary. So we get the meaning of that jargon and we append it to the question. And so yeah, they show this on new hire training documents for engineers, and golden retriever does well on most cases and with multiple LLMs. Yeah, I have a couple more papers on agentic RAG. One is evidence to generate, where we have a single agent for context grounded RAG. So here what we are doing is we have a two-step prompting framework which solves like the slowness of chain of thought reasoning. And yeah, so let's look into what it does. So first, what we do is we specifically ask for the reasoning path or evidence that are mentioned in the context itself. And the context is whatever RAG retrieved. And then this evidence is again passed to a second round of LLM to generate better evidence. And then we have an agent which is classifying whether the evidence supports the claim or refutes the claim. So in evidence to generate, in the evidence tab, we are first from the retrieved context, fetching the exact context. That context we are again giving to generate more evidence, and that is finally given to answer the question. So this is like a two-step process. And some application study is that what sort of evidence are we providing? Like if you only provide the evidence, the score is low, but if you are providing the evidence and the original content, the score increases. And finally, adaptive is selecting on the fly, which gives the best performance. And yeah, and last we have time series analysis. This is a multi-agent system. So if we have time series, then there are multiple tasks on the time series, like it could be anomaly detection or prediction and so on. So here what we are doing is we have a main agent which is routing the task to multiple specialized smaller agents which are fine-tuned specifically for that task, and those smaller tasks are making the prediction. So a query comes, we have this master main agent which is giving a response and routing to the relevant sub-agents. So this is like an agent to route to other agents, and they show it for time series, but could be for anything. Like you are not restricted just to time series. And a couple more enhancements they do is even the prompt is selected dynamically based on the task at hand. And finally, these SLMs, small language models, are trained in an enhanced manner to avoid issues with small language models. Like they usually have a smaller context, so they add enhancement to improve the context and finally train it with PEF. So that was agentic RAG. Any questions so far? Okay, so let's move to graph RAG. Now, why do we need graph RAG? So baseline RAG integrates a vector database, but it struggles with multi-hop reasoning questions. Like we can say, which city was the current president of the United States born in? So this is like multi-hop answer needed, where we first retrieve the president's name and then retrieve which city that person was born in. So GraphRag incorporates knowledge graphs with LLMs, and we have this through knowledge graphs. We have the entity linking, like the relationship in this case between the person and their son's name, and so on. So in GraphRag, what we have is source document and chunking as in vanilla rag. Then an LLM is used to extract element instances, could be like intent, entity, and so on. Then an LLM is used to summarize this element instances and connect them. So we can say that father relationship son of, and then the son's name. So now once we have a relation at the entity level, we are combining multiple entities to create a graph community. So maybe all the former presidents of United States will form a community. Then we have an LLM to summarize the community, and then when a query comes, we can answer based on the community or based on global questions. Global questions could be questions which need aggregation of a lot of data. Probably, yeah, I can just go over very briefly where we are using LLMs to identify all the entities, and we are constructing an initial knowledge graph, and then we are clustering based on communities, and finally summary using an LLM. So in this case, we can do global search about the whole data or the whole community, or local search specific to that particular community. For a global search, we just retrieve the like particular community, and for a local search within the community, we again have to extract the entity, and that entity has multiple aspects, which is used to generate our response. So this is one paper on GraphRag where they are focusing on like query focused summarization. So if the question is what are the main themes in this data set, this is a difficult question for a vanilla RAG because there is no relationship between multiple documents in a vector database, which not at least defined in a vector database. So here GraphRag is combining previous methods with graph, and the exact same process is being followed, which I showed, where documents to chunk, then the summaries, graph communities, and now we have these community summaries. So when a question comes, we retrieve the community summary, then generate an answer based on the summary, and that is used for the global answer. So first, yes, we have the prepared community summaries. Then we map it, where we are also generating intermediate answers, one for each of the chunk. And the LLM is sort of self-reflecting, like which of the chunk is relevant. And the irrelevant chunks are filtered out. And finally, these intermediate answers are sorted and given as context to generate the final answer. So yeah, results show that like which is the most resource intensive approach, and which needs the fewer tokens. So as we can sort of guess that questions related to the root have fewer tokens, and the questions as we go deeper need more tokens. Then we have a medical graph RAG where we need to retrieve medical documents. So obviously for all RAG systems, factuality is necessary, but more so for medical, which is why this paper like proposes a three-step hierarchy where the document is chunked, we extract the elements, hierarchy linking, which is 3-step, where we have the medical reports, the books, and the dictionary. And finally, based on this clustered, we are doing our querying. Okay. And any questions so far? So I hope the usefulness of graph was clear here. And the last type of RAG that I want to cover for today is multimodal RAG, which was also, I think the multimodality was the previous expected talk. So one of the first one is MU RAG, which is like a multimodal RAG. Here we have a pre-trained language model, which is enhanced with a multimodal memory, which contains images, text, and image text pairs. So this memory is a pre-trained T5 transformer and a vision transformer. That creates a backbone of our encoder. And then during the retriever, we take a query and retrieve the memory of M image text pairs using the backbone encoder. And those image text pairs are used to generate our answer. So the encoder is quite important, and because that helps us with the retriever. So it takes image text pairs and during the retriever, the relevant images or text are retrieved. So let's look into the encoder model, where we have the image being encoded with a vision transformer, embedding of the text, and again embedding of images and so on, which creates a sort of multimodal embedding. And this is how it works in runtime. We have a query, we are encoding it with our backbone. Then all the documents are also encoded with our backbone. In this case, the documents are multimodal, and it is retrieving us chunks of images and text. These chunks are augmented with the query, again given to the backbone encoder. And finally, the backbone encoder is like the outputs is passed to a decoder to get the final answer. Is this clear? I can move on in that case. So yeah, so on a web question answering data set, the MU RAG has state-of-the-art performance and outperforms many baselines in accuracy over retriever and so on. And finally, we see that they are pre-training the backbone. So like after pre-training, MURAG has better performance. And lastly, they propose a two-step fine-tuning where we take the in-batch memory and the fixed retriever memory, and having both the stages is better than having both of them independently. Then we come to rule-based multimodal RAG, where again it is for the medical domain. And here what we do is when we are retrieving the documents, we are also giving them a score which tells us the risk, the factuality risk of that document. So if the factuality risk is high, which means more likely that the document is going to be incorrect, then we drop that particular document. And another interesting part is, so far all the RAG techniques, we are going on the assumption that the retrieved documents have better information than the existing knowledge of the LLM. But here they propose that there are cases where even the existing LLM is smart. It knows answers better than the retrieved documents. So they are proposing a balance strategy, a balance between the inherent knowledge of LLMs and the retrieved documents, in case the retrieved documents are incorrect. So using both these enhancements, where we have the factuality risk control on the top documents and the balancing of the inherent and the external knowledge. They train the MED VLM. And we can see that there are some cases where there is over-reliance on the documents, which is wrong. So having a balanced approach helps us. And we can see that this method performs better on question answering on patient's x-rays. And finally, each of both these techniques are important because even if we remove one, the performance goes down. The next is video rag. So in video rag, we have the query and we have to retrieve video. It could be retrieving one video out of multiple videos, or it could be retrieving that particular frame from that particular video. Now videos has lot of frames, and ideally we would want to use all the frames, but that is a very expensive process. So there are some sampling techniques like interval-based sampling, where we just sample one frame per second in a 1K video, or based on the pixel intensity, where we have a histogram of the frame based on the pixel intensities, and then we are comparing how similar two frames are to each other. If they're similar, we keep only one. If they are dissimilar, we keep both of them. And structure feature based, another similar similarity. And finally, we have semantic feature based similarity, which is a neural network based similarity. So each frame we are encoding using ResNet and CLIP, and then we are doing a cosine similarity search. So all the images frames which are similar, we keep only one out of them. So as expected, in most cases, semantic feature based, like the neural network based similarity, outperforms other methods. And but there are some cases where the choice depends on the application. We'll see two such applications. So where we just have to retrieve a video out of multiple videos based on text, we see that the simplest similarity, which is the interval-based similarity, performs the best. And when we are retrieving a particular frame out of many videos, we can see that the neural network-based similarity performs the best. So yeah, then we have another advancement where we have an improvement to ensure the factuality of the reports generated in medical domain. So here we are using a RAD graph, which is a graph related to radiograph, to get similar matching reports, then retrieve the multimodal reports, and then similar embedding search for retrieval augmented generation. In the interest of time, I'll skip details. Yeah, so having this radiograph and the other steps of the pipeline, like and so the radiograph and the report pair mining significantly improves the actuality. Okay, those were all the advancements of RAG that I will cover in today's lecture. Any questions on any of the RAGs so far?
So I have a question about.
I don't know if you can pick your voice from that distance.
I have a question related to corrective rag. They you said like if the information is incorrect, we go to web search to get the results. So how do you ensure like the result from web search is also correct?
So we use the same same evaluator multiple times. Once we have those documents retrieved from the web, we can again use that same evaluator to evaluate those documents and do it in a recursive manner. I can probably quickly bring it up. So yeah, we have this retrieval evaluator. We can use it thrice. Once we are using it on the retrieved documents, then we are using it on the individual strips of those documents. Strip is like just 1 or 2 sentences. And then we are also using it, we can use it on the web documents. I don't think this paper is doing that because they're assuming that the webs, like the internet, has the latest and correct information. Okay.
One
So I'll
question.
spend- yeah.
So when you talk about that, taking the video feed and taking it frames by frames, right? And you said that, giving a time will give you right results, but I'm talking about in a industry where you wanted to check out each image frames for an anomaly or something like that. So how
Yeah.
does it work in that for that use case?
So it's a bigger question of how frequently you want to sample. Now, if your use case is very critical where you need to sample all the videos, you can go ahead. And the thresholds here are also dynamic. So if there is a rare use case where you need to analyze every single frame, then you better have the budget to do so. But in most cases, where let's say if our task is given a bunch of videos, find the video in which the speaker is happy. In that case, maybe sampling just 10% or 20% of the frames would be good enough for us. So it's quite, I would say, use case specific how much you want to sample.
So when budgeting is not a concern and then the sampling is not the right approach, probably we can just analyze each frames and then based on the use case, right?
Yeah. I will need a very high budget to store, to process all the samples, use all of them for downstream RAG and so on. As of now, I can't think of a real world. Okay, maybe if NASA wants very high precision in their space research, they might create the budget to sample everything.
Thank you.
Okay, so I have 2 more topics to go. I'll spend probably 5 minutes on each. One is RAG evaluation. So we had so many RAG techniques. How do we evaluate RAG? So in many cases, we don't have the time to have a human annotated ground truth. So there is a library RAGAS, which is a RAG assessment library. They offer multiple metrics. 4 of them I'm discussing here. For generation, there is faithfulness and answer relevancy. So how faithful it is, like how grounded the answer is in reality and how relevant the answer is. And then retriever, we have standard metrics like precision and recall. And now the how faithfulness is being calculated is we have LLM as a judge. So the LLM is creating the answer and another LLM is judging the answer. Where in faithfulness, the LLM checks that how many of the generated answers can be inferred from the given context. And they train a LLM which is very good at checking the faithfulness. And then there is answer relevancy. So here what we are doing is, given the answer, the LLM generates questions, possible questions, and those list of possible questions, we do a cosine similarity with our original question. If those questions match, then the relevancy is high. So yeah, in this manner, we are using LLM as a judge. Then, so in terms of use cases of RAG, this is one of the research papers I recently worked on, where I'm using RAG for evidence-backed fact-checking. Very similar method to what I covered, the vanilla RAG, where we have a claim, could be any claim, let's say the could be, let's say, the number of COVID cases today. And then we have a knowledge base. So we are retrieving the documents based on the claim. Then we convert the claim into a question, and that question we use on the document to generate the answer. So this is our RAG. And those generated evidences are given to another LLM along with the question to check if the evidences refute or agree with the claim. And like to extract the retriever is straightforward. We just do semantic cosine similarity. Or to extract the evidence, first we convert the question into claim. If the question is Donald Trump has stated he will not contest for next election, it will be converted into a question where did Donald Trump state he will not contest the next election? And then this question is given along with the document to generate an answer. So this answer for 3 documents is concatenated to get the final class. So there is a recent paper that we worked on, and the code and paper are available online. Finally, I come to the last part of my talk, which is like we covered a lot of theory and advancements. Let's look at how RAG is helping in the real world. It is being used in customer support systems. I think we already saw in one of the papers where it is used for the customer support chatbot. Benefits are like consistency, cost, and so on. Search engine, Google has come up with an experimental feature where the answer is displayed on the top. So here, instead of going through all the links, we directly get the answer, which saves our time. And it can be used for content generation if you want to do some content research for a company and so on. Medical industry has many use cases. I think some of them we already saw. It could also help with like diagnosis assistants where we are questioning multiple patient records and papers, summary of medical literature, drug discovery. Then it could be in ticket management system where the RAG analyzes the context, extracts keywords, and then understands the issue, categorizes it. So the incoming ticket also needs to be routed to multiple categories, and finally we can have a human or an AI agent to solve the ticket. Personalization is another interesting use case. So if a company wants to run a marketing campaign, then the factual things are going to be same for everyone, the products and offers of the company. But instead of sending the same email, you can use an LLM to generate personalized emails based on the retrieved facts. Then it's used in finance, education, enterprise knowledge management, which I saw. One of my favorite use cases, code generation, because we are using a RAG to write the code for RAG, where we can, like, given the natural language description, retrieve the similar code snippets, predict next code, generate documentation, and generate test cases based on the given input and historical content. And these are just very few applications that I covered. It is being applied everywhere in e-commerce, legal research, sports, sales automation, and so on. So yeah, to conclude, RAG helps us get the latest information to the LLM and reduce hallucination. We surveyed some advanced techniques like agentic RAG, multimodal RAG, and so on. Along with routers and agents and graphs, RAG offers us a very rich and effective framework to solve many tasks, way beyond simple question answering. And we also saw some real world use cases where it is actually being used. Finally, a disclaimer that this is not an exhaustive list by any means. Please go read more topics and please read the related papers and research. I could cover them only superficially given the time. And yes, I'd like to thank Professor Shade and Amitav sir to give me the opportunity and some of my friends who helped me create these slides. So yeah, any questions on any part of the talk, anything that is not clear, any doubt, any suggestions, feel free.
Parth, thank you. This was probably too much material for um, uh, one lecture, one seminar. But let's start with the generic question. RAG was all the rage last year.
Mhm.
Is it retaining its value, or people are losing interest in RAG and something else is coming?
So from my experience and some readings, I can say that RAG is already a bit older. Agentic AI, agentic LLMs, and agentic RAG is all in like the hot race right now. So I think most of the current use cases and the cool startups which come up are market pitching themselves as an agentic AI company rather than vanilla RAG.
And do you think the agentic AI approach is more principled, more rather than just engineering thing, throwing more stuff
Yes.
outside of the training, or is it also going to be unprincipled things, trial and error that will be hard to have something very foundational and clear. I mean, we used to do multi-agent workflows 25 years ago, distributed workflow, adaptive workflow, work coordination, all kind of things we're doing. Of course, we did not have the generative AI kind of component at that time. So those agents were more programmatic agents or the task agents and all that. We used to have variety of agents also. I have a paper on collaborative agent, cooperating agent or collaborative agent in 90s. Okay, so is agent thing more organized? Are there good evaluation things, or is just an engineering also thing, a new kind of envelope with the same mess inside?
It's a lot of engineering to make LLMs powerful. Like routers can tell you which tool to use, but an agent can go ahead, use that tool, and pull in the results and use it for further evaluation. Agent can do a lot more. Like it can, given a whole complex task, it will decide subtask, route it to relevant agents in a multi-agent system. So it is definitely a lot of engineering, but I think some theory from the older previous research that you were talking about on multi-agent systems is being pulled in for evaluation and inspiration.
Okay, because sometimes I see all these very heavy words, but underneath, there are a lot of limitations. Anyway, sounds good. You guys have any question? Generally, maybe some people are here interested. Last year, everybody, of course, the hiring has been not too good in the, you're well aware of that. But last year, almost all advertisement talked about LLMs. How is that changing?
I think there's still a very high traction in LLMs. Again, the same thing applies. Like LLMs might be slightly older. More of the recent companies want to do agentic LLMs. Agentic LLMs, I think, is in the early stage of their hype curve. And I see a lot of openings at many companies just for LLMs, prompt engineering, or recently agentic AI. I personally, I think huge scope, and it is actually generating values to end users and enterprises.
Hmm. Okay, guys, you want to ask any question? Are you? No? All right. Well, I think we did use up our time. Thank you very much, Parth.
Thank you very much,
Thank you.
Dr.